All right, so here's the deal. We're in chapter 3 now. Let me go over here. Maybe it was off the record. Who knows? All right, so I hit the pause button now. Now we're resuming here. All right, so again, like I said before, I will be getting back your test on Thursday. So here's the deal. We're in chapter 3. Chapter 3 is going to be looking at different other types of functions and us taking the derivative of those things. And the other types of functions that we're going to be focusing on are 3 different kinds of functions. The first one is exponential, the second one is going to be logarithmic, and the third one is going to be inverse trig stuff. Inverse functions, and especially focusing on inverse trig, sine inverse, cosine inverse, tangent inverse, arc sine arc, cosine arc tangent. So the way I've set up these notes is this. Now you are supposed to have covered logarithms and exponentials and inverse functions and stuff like that in your high school algebra 2, algebra 1 courses and stuff, but it may have been a while since you've done that. So what I have done here is this. I have what I call chapter 3 review. It's just reviewing sections 3.1 and 3.2, focusing on the algebra aspects. Then I've created another section 3.1, which is focusing on the calculus aspect, knowing all the algebra. And I did the same thing for section 3.2. So the ones that I've labeled 3.1 and 3.2 are focusing on the calculus, but not sure of your backgrounds and stuff. I've created this section 3.1 and 3.2 review just to go over the algebra. So again, it depends on what your background is and the like. So this first section, we're not going to be focusing on calculus. We're going to be focusing on algebra, making sure you got that background first before I do the calculus. So here we go. Definition. A function f of x is 1 to 1 if every element in the range corresponds to exactly one element in the domain. That means that if f of a equals f of b, then a had to be equal to b. Or also, if a does not equal b, then f of a would not be equal to f of b if I have a 1-to-1 function. Now, most people don't remember the definition of 1-to-1 function, and that's normal. What they do remember is this, the horizontal line test. Horizontal line test. If there is no horizontal line that intersects the graph more than once, then the function is 1-to-1. So this is your visual perspective of how to test for a 1-to-1 function. 1-to-1 functions, you have a vertical line. If a vertical line only intersects the graph at one spot, then it's going to be a 1-to-1 function. If it intersects at more than one spot, it is not going to be a function. So, determine whether these functions are 1-to-1. F of x equals x squared plus 2. X squared plus 2, what kind of graph does that look like? Parabola. What is that plus 2 going to do for me? Shifts it up 2 units. There it is. Is this thing 1-to-1? Yes or no? Well, I hear 2 things, yes and no. Well, see, the problem with that one is this. To figure out if you have a 1-to-1, and that's my standard notation for it, 1-1 function, you've got to use the horizontal line test. Now, motion with your hands what a horizontal line looks like. Yeah, it's not this one, it's this one. So this is what we call a horizontal line. So if I draw a horizontal line in there, how many times does that intersect that graph? In this case, twice. Okay? But if it's a 1-to-1 function, how many times should a horizontal line intersect the graph? At most, once. So is this thing 1-to-1? No. Not 1-1. This is not a 1-to-1 function. What about this graph over here? G of x equals x divided by x minus 2. So it's time for the calculator on this one, but let's see what this thing looks like. F of x equals x divided by parentheses x minus 2. And I'm going to hit the old zoom 6 here, and it looks like this. And we typically call this guy, oh, I'm out of battery power here. This is not good. All right. We typically call this guy a hyperbola. The question is this thing 1-to-1? Horizontal line. any horizontal line you pick. How many times intersect the graph? Once. So is this thing 1 to 1? 1 to 1 question mark? The answer is yes. This is a 1 to 1 function. Okay? Now why do you care? Well, the next concept, again, all this is algebra. This is stuff you're supposed to have known from previous math classes. I'm just taking it as a big review day here. Let f of x be a function that is 1 to 1 and that goes through the point A, B. Then f with a little minus 1 of x called f inverse of x is the inverse of f of x. Okay? And what do we mean by inverse? Well, this is all the things we mean. Properties of inverse is if I take the composition of f composed with f inverse of x, I get x. F inverse of x will go through the point BA. Here's what inverses do. If you got a point AB on f, then the point that's going to be on f inverse will be BA. What it does is it switches the x and y coordinates. What it does in English means that it is switching the domain and range. It's switching the independent variable and the dependent variable. So if I have a function, a 1 to 1 function, that if I input number of units produced and the output is profit, the inverse function would be the input would be profit and the output would be the number of units I produce. It switches that independent dependent variable concept here. Okay? The domain of f of x will be equal to the range of f inverse of x, and the domain of f inverse of x will be the range of f of x. When I switch the x and y, the a and the b here, it's also going to be switching the domain and range. The reason why is this. Look at your steps of finding this inverse function. To find an inverse function, finding inverse, and the key word here is functions here. So you can always have an inverse relation. Just switch the x and y and you got an inverse relation. But when that inverse relation is also a function, the only way that happens is when it has to be a 1 to 1 function. That's why the steps are what they are. Step number 1, test to see if the function is 1 to 1. Because if you don't have a 1 to 1 function, the inverse will not be a 1 to 1. The inverse will not be a function. Then step number 2, replace f of x with y. Step number 3 is actually the step that actually gets the inverse into it. Interchange the x and y. Switch the x and y coordinates. Then solve for y, and then at the end replace y with f inverse or g inverse or whatever you call the original function. Okay? All right, so again, this is all algebra review. Now going back up here, these are my tests for inverses and stuff. So, here's a question. Verify that the functions are the inverses of one another. To test to see if they're inverses of one another, you have two options. I can either take this guy and use my steps of finding inverses, and this function should pop out. Or the other one is this. Only inverse functions have the property that when I take f composed with g of x, after I clean it up, x will pop out. So here's the real test. It's actually a theorem that I'm using to test for inverses. So what I'm going to do here is I'm going to take the composition of f composed with g. This is f of g of x. F is on the outside, g of x is on the inside. F is on the outside, that looks like the cube root of something plus 4. F is on the outside, so it looks like the f function. You're replacing the x with the entire g of x function, which is x cubed minus 4. Now clean it up. Well, I can drop that set of parentheses here, so that's the cube root of x cubed minus 4 plus 4. Working inside my parentheses, you'll notice that the minus 4's cancel. Minus 4 plus 4 cancels. And I'm left with the cube root of x cubed. The cube root of x cubed cancels, and I'm left with x. And when I get x out of it, I can therefore state that f of x and g of x are inverse functions. Does that make sense? This is a nice little theorem to have in your back pocket when you're asked to test to see if these guys are inverses or not. Okay? Turn page. Now, look at the directions. That's really what you're paying attention to with these particular set of notes. Example, find the inverse of the following. K of x is equal to x minus 1 quantity cubed. All right, here we go. X minus 1 quantity cubed. Step number 1, you want to graph this guy and make sure it's a one-to-one function. What does x cubed look like? What does that graph look like? It's a squiggly line. You should know your cubic graphs. But what is minus 1 going to do? Which direction is x minus 1 quantity cubed? With that minus 1, which way is it going to take it? Is it going to take it to the left or right? To the right 1 unit. So this is what the graph looks like. Is it one-to-one? That's the question. Well, any horizontal line only intersects at how many spots? Once. So the answer is yes, it's one-to-one. So there's your first step. The second step is replace function, in this case k of x, with y. I get y equals x minus 1 cubed. The third step is actually the inverse step. What you're supposed to do with step number 3 is switch x and y. This gives you x is equal to y minus 1 cubed. Step number 4, solve for y. That's the algebra part. How am I going to solve this thing for y? What are you going to do first? Factor. Well, factor, I want to get y by himself. I could fold this thing out, but cubic, that's just going to make it even nastier. I want to get y by itself. So in other words, I want to kill off this cube. What kills off cubes? Take the cube root of both sides. This will end up canceling, leaving me with the cube root of x equals y minus 1. Now, solve for y. What would you do? Add 1 to both sides. So y is equal to the cube root of x plus 1. Does that make sense? And then the step number 5 is just the fancy thing. What was this original function called? The original function was called k of x. So therefore, this is my inverse. You replace y with an inverse notation. K with a little minus 1 on it of x. K inverse of x. That's equal to the cube root of x plus 1. And there's my answer. All right. The second one is the one they love to give on the old final exam. They love this problem because of all the algebra you have to do in solving for y. So, pay attention to this particular problem here. First thing you want to do is step 1 is make sure that function is one-to-one. Because if it's not one-to-one, then you don't have an inverse function. So this is parentheses 2x minus 3 divided by parentheses x plus 1. Zoom 6 it. It looks like that. Now, we've seen a problem that looks like this before. Is it one-to-one? Any horizontal line only intersects at one spot. So the answer is yes. So you can continue. Step number 2 is replace, I'll just put S2. Replace function with y. It gives me y equals 2x minus 3 over x plus 1. Step number 3, switch the x and y. Put a star by this guy because this is the most important step. This gives you that inverse. X is equal to 2y minus 3 over y plus 1. Wherever there was an x, put a y. Wherever there was a y, put an x. Switch the x and y. Now, here's the algebra. Step number 4. We want to solve for y. What's your first move to solve for y on this thing? I want to cross multiply or multiply both sides by y plus 1. Get rid of your fractions. This gives you x times y plus 1 equals, here the y plus 1's cancel, leaving you with 2y minus 3. The next thing you want to do is you want to distribute. This gives you x times y plus x equals 2y minus 3. You're solving for y. Keep your eye on the ball. So here's a y and here's a y. I'm going to get all my y's on one side. So I'm going to subtract 2y from both sides. This cancels. These are not like terms, so I can't combine them. this becomes xy minus 2y plus x equals negative 3. I'm going to add 2y to both sides. This cancels. It gives me xy plus x equals 2y. I'm sorry, I went back. I went wrong one. Subtract x. Thank you. Minus x on both sides. There we go. So if I subtract x, that gives me 2y minus xy minus 2y equals negative x minus 3. Let me rewrite that again. xy minus 2y equals negative x minus 3. Now, what are you trying to solve for here? Y. You're trying to solve for y. You've got y's in multiple terms. So factor out the y. That gives you x minus 2 equals negative x minus 3. I'm going to divide, and that gives me y equals negative x minus 3 over x minus 2. There it is. See, this is why they love this problem so much, is because of all the algebra that you had to do on it. Now, here's my question for you. What was the original function's name? G of x. So the last thing you want to do is replace y with the inverse notation. Therefore, g inverse of x would be equal to negative x minus 3 over x minus 2. There's my answer. Does that make sense? Watch the algebra. And again, I promise you will see another problem like this on your next test or in homework, and they're going to throw one of these guys, they always do on the final exam, because it's good algebra to be able to solve for x in terms of y. The idea of multiplying both sides by your denominator, distributing, collecting y terms on one side, x terms on the other, and then factoring out the y and then dividing. Look at number 3. Again, find the inverse function if it exists. H of x equals x squared plus 3. So what is h of x equal x squared plus 3? What does that look like? That's a parabola shifted up 3 units. There it is. Okay? Is it 1 to 1? No, it's not. So therefore, your answer is this. Because it's not a 1 to 1 function, there is no inverse function. Now you can always switch to x and y and knock yourself out. That would give you, x equals y squared plus 3. But that guy is not going to be a function. And the reason why is, remember, functions is the vertical line test. So there you go. All right? Again, this is all algebra review. Questions? All right, next one. Yes, sorry.
Could you show us where is it possible to have a one-to-one relationship with a square, an x squared in the...
Yeah, well, you have to do something called a restricted domain. If I wanted to make this guy a function, so it would have an inverse function, I would have to do something like this. H of x would be equal to x squared plus 3, and I would have to state x had to be greater than or equal to 0. I have to do a domain restriction on it. So what would that parabola look like? Well, it's a parabola, but you only get the graph for x is greater than or equal to 0, so it's this half the graph. Does that make sense?
Right.
And therefore, this would be a 1 to 1 function because I'm only allowed to graph this half. So then I can continue on with my steps and then take the square root of both sides. See, with the square root, you've got a problem unless you have a restricted domain because of the plus minus issue.
So I guess what I'm saying is that any equation that has x squared in it is not going to have an inverse function.
Unless you have a domain restriction. And that also includes all even powers. X squared, x to the 4th, x to the 6th, so forth and so on. Odd powers, clearly, like this one up here, odd powers, you just definitely had an inverse function. All right, continuing on. The graph of f inverse of x can be constructed by the mirror of the graph of f of x over the line y equals x. All right, so let me show you this guy. Let's take a look at this function. F of x is equal to square root of x. Now that's a function you guys should know. Square root of x. What's the square root of x? Well, when you graph it, you can only graph the positive terms because you can't take the square root of a negative number. So you can start with 0. Square root of 0 is 0. Square root of 1 is 1. The square root of 4 is actually 2. So this is my picture of f of x equals the square root of x. Now I'm going to try to draw this with my wonderful red pen thing here so you guys can see. Now, I'm going to put the particular y equals x axis. The y equals x axis actually is a line that splits the first and third quadrant. The y equals x axis. Now, like I said before, if you want to figure out what the graph of the inverse is going to look like, you draw this y equals x axis, and then, I'm going to switch it on its side here, and then you do the reverse image. So this was the point 0, 0. Well, the inverse, switch x and y coordinates, still 0, 0. This is the point 1, 1. When you invert it, you switch to x and y, still 1, 1. This point was the point 4, 2. So if you switch it, it would become the point 2, 4. And if I connect my dots accordingly, you actually get to see this idea of symmetry in the reverse image here. Symmetric with respect to the y equals x axis. And this function up here would be f inverse of x. That would be what the graph looks like. Okay? So, anytime you've got a function, you just take the points and switch to x and y coordinates and replot it. That will give you the inverse function, and it will always be symmetric to the line y equals x. Number 2, the following points of the function. I got f being equal to the points 2, 10, negative 1, negative 3, 0, negative 2, 1, negative 1, 3, 6. Find the points of f inverse of x. What are they going to be? This is drumming home an idea. What's the first point going to be? 10, 2. Next point? Negative 3, negative 1. The next point? Negative 2, 0. The next point? Negative 1, 1. And the last point? 6, 3. All I did was switch the x and y coordinates. And again, reminding you of the ideas. The domain of f of x ends up becoming the range of f inverse of x, and the domain of f inverse of x is the range of f of x. A function f of x has the following graph. Find the domain and range of f inverse of x. Okay? And so what I'm going to do is I'm actually going to put little dots at these points right here. Okay? Filled in dots. Doesn't really show up when I print these things out. So, what is the domain of f of x? What is the range of f of x? What's the domain of f of x? Domain by definition is what?
X values.
X values. What are my x values? Because this is a filled in dot. This is negative 1, negative 2. And this goes all the way out to here's negative 1, here's 0, 1, 2, 3, 4, 5. So where does it end up at? 4.5. So the domain, using pointy brackets because I hit the numbers, is negative 2 to 4.5 bracket. The range are the y values. So this is negative 1, negative 2, negative 3. Here's 1, 2, 3, 4, 5. So what is my range? It is going between bracket, because I hit the point down here at negative 3, all the way up. It's the only time I ever used the y coordinates. All the way up to 5. Bracket. Now, I'm not asking you to graph this thing or anything like that. I'm just asking you this. What is the domain of f inverse of x? And what is the range of f inverse of x? What is the domain of f inverse of x? No. No, that's not negative 4.5. You don't switch the numbers or anything like that. The domain of f of x becomes the range of f inverse of x. That's right. And negative 3 to 5. Because the range of f of x is the domain of f inverse of x. And what's the range of f inverse of x? Negative 2 to 4.5. The domain becomes the range, and the domain becomes the range. Okay. Now, moving on to the next concept. Again, I am trying to kind of shotgun this thing and give you all the algebra before we get to the calculus of this stuff. So let's review a little bit of exponential and logarithmic notation and stuff. Definition. An exponential function is a function in the form of f of x equals a to the x, where the variable x is in the exponent. Find the x for each of the following. Solve for x here. 4 is equal to 2 raised to x. What does x have to be equal to? 2, because 2 squared is 4. 27 equals 3 to the x. What does x have to be equal to? 3 to what power equals 27? 3. All right, here we go. 2 equals 4 to the x. What value of x do you have to get 2? 4 raised to what power equals 2? What's the relationship between 4 and 2? Well, the square root of 4 is 2. But we don't do square roots. What's a square root? That's why it's a half a power. So that would be x, it would be a half. Now, these are, when you look at these particular parts as functions here, these are exponential functions to the variables in the exponent. Now, here's the problem. When you're trying to solve for those exponents, this new function was developed. It's called a logarithmic function. A logarithmic function is a function that helps us to solve and I didn't mean the word quadratic, it should be exponential equation. That's my typo there. Exponential function. Logarithms allow us to isolate the variable in the exponent. Cut, copy, paste thing just kills when you copy the wrong thing. Exponent, okay, and the other way around. So the first thing you need to know is what I call the smiley face definition of logs. Because let me explain it this way. How many years you guys been working with exponents? What grade did you guys first start talking about exponents? You know, like 2 squared and things like that. Yeah, about 4th grade maybe. Yeah. Depends on what school you were at and how slow you were, but whatever. Okay. But about 4th grade is when you should have. 2 squared, 2 times 2 and stuff like that. But whatever. Could have been high school for some of you people. I don't know. But my point is this. You've been working with exponents since about maybe 4th, maybe 6th grade, depending on the new math and stuff like that. But here's my question. When did you guys start studying logarithms? What grade was it that they introduced the logarithm to you? No, it would have been never. It was a requirement. You had to have it by law. But it was about, 11th grade maybe, 12th grade? So here's my point. You've been working exponents your whole life, for the most part. You've been working logarithms only the latter part of your life when high school, about the 11th grade or so. Okay? So here's the nice thing about logarithms, because logarithms tends to bother a lot of people because you haven't been exposed to it that much. You have something called what I call the smiley face definition. You would read this. Y equals the log base b of x. Y equals log base b of x. Here, b is the base and x is the number. But this is the definition of logarithm. If you ever have log base b of x equals y, you have the ability to rewrite logarithms. So if you don't like this form here, this is what you do. You start with the base, b. You raise him to the other side, b raised to the y. It equals what you're taking the log of. It equals x. And it makes a little smiley face type thing here. Okay, so base raised to the y equals x. My point is this. This log base b of x equals y and b raised to the y equals x is the exact same equation. This is written in logarithmic form. This is written in exponential form. It's the same equation. The purpose of logarithms, the reason why you studied logs in the 10th, 11th, 12th grade, whatever it happened to be, was this. This is important. Get it in your notes. Logarithms solve for exponents. When you got a variable in the exponent, which you're soon to have, and you need to solve for this thing, logarithms solve for exponents. This is why we study them. The purpose. When I have a variable in the exponent, I need to solve for it. First thing that comes to mind is logarithms. So, turn back. Solve these logarithmic equations. X is equal to log base 2 of 16. Well, that confuses people just looking at that. As again, x equals log base 2 of 16. If you don't like it, rewrite it. So, What is x equals log base 2 of 16 also known as? 2 raised to the x equals what you're taking the log of, which is 16. Well, that's an easier way to handle it. 2 raised to what power equals 16? 4. Let's see here. 2 to the first power is 2. 2 squared is 4. 2 cubed is 8. And 2 to the fourth power. That's 2 times 2 times 2 times 2. And that's 16. And so x had to be 4. All right, look at number 2 here. Y equals the log base 6 of 216. If you don't like this one, rewrite it. B, all right, in this case 6, raised to the y, 6 to the y equals 216. Well, let's see here. Well, let's see what you know. What's 6 to the first power? 6. 6 squared is what? 36. What is 6 cubed? 216. So what must the power have been? The power must have been 3. Y equals 3. So log base 6 of 216 actually equals 3. What about the next guy? 3 equals the log base b of 27. If you don't like it, rewrite it. Base raised to the side, b raised to the third power, equals what you're taking the log of, 27. What kills off a cube? Take the cube root of both sides. Solve for b. b is equal to, what's the cube root of 27? 3. b equals 3. But, here you go. 8 raised to the y equals 300. 8 raised to what power equals 300? Well, let's see here. 8 to the third power is 512. 8 to the second power is 64. So 300 is somewhere between 64 and 512. So I'm thinking about 2.5. But I need it to be more accurate than that. If you want the most accuracy, remember, logarithm solve for exponents. You have the ability to go both ways with this street. So if 8 raised to the y equals 300, this is the same form as b to the y is equal to a. I can rewrite this as the log base b of a equals y. So I can rewrite 8 to the y equals 300 as the log base 8 of 300 equals y. Doesn't look like a nice number, but don't worry, we'll show you how to use your calculator to get that converted into a decimal in a few minutes here. Does that make sense? Now, logarithms have properties. Here are some of your properties here. First property is this. The log base b of b equals 1. To explain this, use the smiley face definition. b raised to what power equals itself? 1. Remember, logarithm solve for exponents. This is the first power. b to the first power equals b. b raised to what power equals 1? What's going to kill off every number regardless of what the base is? b raised to the 0 power always equals 1. So log base b of 1 has to be 0. But look at this next step. The log base b of 0 equals what? Well, does not exist because b raised to any power is you're never going to get 0 out of that thing. So it does not exist. You can't take the log of 0 is what this is saying. I don't care what the base is. But look at these other guys. You've got this one. Log base b of b to the x equals what? It equals x. Reason why? Two things. b raised to the x equals b raised to the x. But what you should also be seeing is this. Logs and exponentials are inverses. They're inverses, so they end up canceling each other out. The log base b of b raised to the x. The log base b and b to the x cancel each other out. You're left with x. b raised to the log base b of x, because logs and exponentials are inverses, b raised to the log base b of x will also cancel each other out. And there's this other one. This guy right here. log of x. The problem is there's no base written. That is because we don't write a base when it's understood to be base 10. This is called the common log. Because our numbering system is base 10, we got so lazy in mathematics that we just write log and just stop writing the base 10, because when you see a log without a base, it's understood to be base 10. Okay? So, on your mark, get set, using your properties, go. What's the log base 2 of 2? 1. Number 2, what's the log base 6 of 1?
X.
No, it's not x here. Wrong one. I'm number 2 here. Log base 6 of 1? 0. Here we go. Log base 4 of 4 to the x? X. Log base z of z to the x plus y? Because the log with the same base as the exponential cancel, you're left with x plus y. All right? 8 raised to the log base 8 of 12y. 12y. Again, exponentials and log of the same base are inverses. They cancel each other out. You're left with just a number. What's the log of 10? Very good. It's 1. But the log is actually a button on your calculator, and it's located right here. So if I turn this thing on and hit log 10, because we have a log button, but that seems to be the only one. There's another log button called natural log. It's just below it. The log of 10, there you go, you can see it. Log of 10 is 1. Now, speaking of that other button, and this is the one we really get into engineering calculus all about, is the ln. All right, log base e of x, and which is equal to the natural log of x. Definition: e is a number that is approximately equal to 2.718281828, and it's got a never-ending decimal. Okay? This is a number that shows up in nature naturally. E, 2.71828, yada, yada, yada. And there's a reason why it shows up in nature naturally. Now, you've no doubt have discussed this E formula function, this number, in your algebra classes, your pre-calculus classes. May I make an example of something we're going to get to in just a few seconds here? The PERT formula. Have you ever heard of the PERT formula? A equals PE to the RT. That's used when you have exponential growth, populational growth, compound interest, compounded continuous interest. It's a bunch of different algebra that you used in your class. And they all had this E number that you no doubt have seen before. It's just a number, 2.71828. It's nothing but a number, all right? But it's a special number because you'll see why in a second. All right, so because this is such a special number in science, there are a couple of different what we call special numbers in science that just show up in nature naturally. The first one is pi. What's pi? 3.1415926 ... keeps on going forever and ever and ever. When do you use pi? What concepts do you study? Circles. Circumference of a circle, 2 pi r. Area of a circle, pi r squared. Volume of a cube, volume of a sphere, excuse me, is 4/3 pi r cubed. So you see pi with circles, all right? This E number is another number that shows up in nature naturally, and it usually deals with growth or decay type of problems. Money grows, so those people that are planning on going in business or whatever, they'll see this E number quite a bit as well, because money grows like populations grow. So, because this guy is so special, we don't typically write log base E. We give it a special notation, ln x. ln, log del natural, some French thing here. But ln, natural log, is how we pronounce this. You kind of read it this way, natural log. But here's my problem. I've had so many students tell me this. ln, they call it line x. I have never heard that until a couple years ago. And I had a bunch of students come by. And the only thing I can figure out is your high school teacher must have been pathetic, because it is not a line, it's a logarithm. Log x. Don't call it line. Don't line me, because I will fail you. Log x, natural log of x, is what this thing's all about. It's not a line. It's ln, standing for natural log. So basically all we want you to do is, we don't typically, it's understood that log base E is natural log, but you notice we don't write the base down here because it's understood to be E. So log base E of 3z is the same thing as the natural log of 3z. And here, what is the natural log of e? Very good. It's 1. Why? Because, remember, natural log is the same thing as log base e of e. And according to my properties up here, the log base b of b equals 1. Therefore, the log base e of e is also going to be equal to 1. All right. Major properties of logarithms. Properties of logs. Here we go. The log base b of m times n is equal to the log base b of m plus the log base b of n. Multiplication turns into addition. Log base b of m divided by n is the log base b of m minus the log base b of n. Division turns into subtraction. And then the third property, log base b of m raised to the n is the same thing as n times log base b of m. Powers get to go out front. These are your log properties. Let me explain why they are what they are in basic, straightforward language here. Logarithms are the inverses of exponentials. Being they're the inverses of exponentials, they act like exponentials. Exponents. Let me talk to you guys about it. What's your property here? All right, let's talk about exponents. If I have a to the m times a to the n, what do you do with bases that are alike? What do I get to do with the exponents? Add them. This is a to the m plus n. Multiplication with like bases turns into addition. Let's talk about division. A to the m divided by a to the n. As long as the bases are alike, division, what do you do with the exponents? Subtract. Top minus bottom, m minus n. And the third one was a to the m raised to the n. A power raised to another power, what do I get to do with the powers? Multiply a to the m times n. Okay? These are properties that we've been discussing since about the 4th or 6th grade or whatever. Multiplication turns into addition of exponents. Division turns into subtraction of exponents. Power to a power, you multiply. Now look at that concept in terms of logarithms. Since logarithms solve for exponents, they act like exponents. The log base b of m times n is equal to log base b of m plus the log base b of n. Remember, logarithms solve for exponents, so they act like exponents. So when I multiply, I end up adding their exponent type concept here. It comes from this property here. This is division. The log base b of m divided by n, that's equal to log base b of m minus the log base b of n. Division turns into subtraction, just like with the powers. And look at your third case. Log base b of m raised to the n. M raised to n is like a power raised to another power. And what do you get to do with that? Well, the n pops out front, so you can multiply n times the log base b of m. Power to a power, you multiply. So, here's where it gets interesting to see if you guys remember your log properties. On your mark, get set, go. Simplify this. Log base x of x times z. Well, that's multiplication. What does multiplication turn into? Addition. This would be the log base x of x plus the log base x of z. But we're not done yet. What is the log base x of x? When the base and the exponential, or what you're taking the log of are the same, they cancel. What are you left with? 1. The answer is 1 plus the log base x of z. That's what it would be simplified. Number 2, the log base 3 of 27. Well, fact is 27 is 3 cubed, right? 3 times 3 times 3. But when the base on your log and the base of the exponential part are the same, they cancel, so we're left with the exponent 3. Same reasoning here. The log 8 raised to the log base 8 of 12y is 12y. And the same idea here. Log of 10 raised to the x plus y. Well, this is understood to be log base 10. So they end up canceling and you're left with x plus y. Look at the directions. That tells you what to do. Expand the following logarithms. All right. Well, if I'm working this problem, I'm going to work order of operation. I'm going to clean up inside the parentheses. What exactly is x times y quantity cubed? That'll be x cubed times y cubed. So that's the log base b of x cubed times y cubed. But what does multiplication turn into? Addition. This is the log base b of x cubed plus the log base b of y cubed. But you're not done. Logarithms shouldn't have exponents, because if it has an exponent, according to property number 3 up here, where do exponents get to go? Out front. So clean up log base b of x cubed. What do you get? 3 log base b of x. And to clean up log base b of y cubed, it's plus 3 log base b of y. Exponents pop in front of the logs. And there is my cleaned up version. Similarly, log base b of x times y cubed. This is multiplication. That turns into addition. Log base b of x plus the log base b of y cubed. And I got a power. Power pops out front. So the answer is going to be log base b of x plus 3 log base b of y. Here's my solution. See if we can make them a little harder. Try this one. The log base b of x cubed times y divided by z squared. Well, this is multiplication division. Numerator is multiplication. Multiplication turns into addition. This is the log base b of x cubed plus the log base b of y. But when you divide, division turns into what? Subtractions. That'll be minus the log base b of the z squared. But you're not done yet, because you got powers. What is the log base b of x cubed? Where does that 3 going to get to go? Out front. So the answer is 3 log base b of x plus the log base b of y minus 2 log base b of z. And there's my answer. Try the next guy. What is, simplify the natural log of the square root of e times x? Natural log of the square root of e times x. First off, I don't do square roots. What is a square root?
Half power.
Half power. And because of strict multiplication division, I can distribute the power. That's e to the 1/2 times x to the 1/2. But it's multiplication. What does multiplication turn into? Addition. So this is equal to the natural log of e to the 1/2 plus the natural log of x to the 1/2. What is the natural log of e to the 1/2 using my log properties? 1/2, because natural log and e's end up canceling. That gives you 1/2. Plus the natural log of x to the 1/2. The 1/2 pops out front. Natural log of x. There's my solution. And again, a lot of these problems I stole off WebWorks, so pay close attention to this. Simplify the next guy. The natural log of x to the 4th times the square root of x squared plus 3 divided by x plus 3 to the 5th. This is equal to, first off, I don't do square roots. Natural log of x to the 4th times parentheses x squared plus 3 to the 1/2 power divided by x plus 3 to the 5th power. Multiplication turns into addition. Division turns into subtraction. This is equal to the natural log of x to the 4th plus the natural log of x squared plus 3 to the 1/2 power. Division turns into subtraction minus the natural log of x plus 3 to the 5th. But I'm not done. These guys have powers, 1/2 power and a 5th power. Where do powers get to go? Out front, and the x to the 4th. 4th goes go out front too. So this will be, the answer is 4 times the natural log of x plus 1/2 the natural log of x squared plus 3 minus 5 natural log of x plus 3. And there's my solution. There's a little note here. This is a John property. The John property is this. The log base b of x plus y does not equal the log base b of x plus the log base b of y. Does not equal. Do not do this. And the reason why is you don't get distribute logs. Do not distribute logarithms. You can't do it. It's an illegal move. Yeah.
Why didn't you, for the exponent within, it says x squared plus 3, you don't drop that 2 down and make it 2x?
Because there's a plus right here. And the only way, the property says, good question. The property says this, that I have, the natural log of x to the n. Then when this guy has a power, the n gets to pop out front. The power's on the x, but the problem is you got that plus 3. So you can't bring down the 2 because the plus 3 is blocking your shot, basically.
Okay, so
You gotta have a single term raised to a power to be able to do that.
what if they both had powers? What if it was x squared plus 3x squared?
Well, then I could factor out an x squared. Actually, you can clean it up. X squared plus 3x squared is 4x squared.
Okay.
Then you can do natural log of 4 times the natural log of x, plus the natural log of x squared, multiplication division, and then the 2 would pop out front. As long as you get a single term to a power, those are the guys that get to pop out front. When you got sums and differences, you got to leave them alone because you can't distribute. Hmm? All right. Let's take a look at this guy. This is us again, a problem off of web work. It tends to freak people out. It says simplify. So here we go. And the way you guys need to look at this stuff, this is just playing games because this is algebra games, but I'm going to explain the mathematics to you guys in just a second. But the way I look at logarithms is this. It's the Humpty Dumpty problems. What's the deal on Humpty Dumpty? He fell off the wall and he broke into a bunch of pieces, and then what was your job? Put him back together again. So, here's Humpty Dumpty. Your job is to take a baseball bat and bust him up into a bunch of pieces. Here is Humpty Dumpty in a bunch of pieces. Your job is to put him back together again as a single log. This is what you're doing with logs. You have the ability to take logarithms and bust him up, and to take multiple logs and put him back as single terms. So pay attention to directions. And then I'm going to explain it from a calculus perspective in just a second after we do this. This is the log of 100 times x plus 3 divided by z times x minus 4 quantity cubed. This is multiplication. Multiplication in the numerator. This becomes a log of 100 plus, multiplication turns into addition, the log of x plus the log of x plus 3. This is division. This turns into subtraction. Minus the log of z minus the log of x minus 4 cubed. Okay? Now let me pause here for a second. Again, I know this is a bunch of review for you guys, but still. Here we go. I know you guys are looking at that minus right there. All right. You're saying, well, shouldn't that be a plus? Because this is multiplication. And you are right in one sense. You're looking locally and not globally. Locally, that's multiplication. Globally, where is that x minus 4 cubed located at? Under the division mark, in the denominator. And if you're in the denominator, you're being divided. And division turns into subtraction. That's the real deal here. Now, let's clean this up here. What base is on these logs? Understood even though I didn't write it down? 10. So this is the log of 10 squared plus the log of x plus the log of x plus 3 minus the log of z minus the log of x minus 4 cubed. All I did was change my 100 to 10 squared. The reason why is because these are understood to be base 10s even though we don't write them down. And what is the log base 10 of 10 squared? Well, when the exponent and the log are the same, they cancel. What are you left with? 2, because the log canceled out. Plus the log of x plus the log of x plus 3 minus the log of z minus 3 times the log of x minus 4, because terms to powers, the power gets to pop out front. And that is my solution. Does that make sense? Question? Yeah.
Yeah, just going back to what you were saying about that minus sign.
Yeah. Yeah. So if you really wanted me to,
line,
right, if you really wanted me to, if you look at this bottom, it's minus parentheses, the log of z plus the log of x minus 4 cubed. But that negative is going to distribute because he's in the bottom, and then we're back to where we started from. And it just saves an extra step. And that's what I'm saying. Look, you're looking locally where you're going to have to distribute the negative, but globally, he's in the bottom. Bottom means divide, divide turns into subtraction with logs. All right, so there's Humpty Dumpty. Here's our baseball bat. We beat him and beat him and beat him, and there is the multiple parts that he turned into. Now, we're working backwards. Rewrite as a single log. Put Humpty Dumpty back together again. So, 3 log base b of x plus 4 log base b of x. I'm sorry, this is z there. 3 log base b of z plus 4 log base b of x. Now, if you go back and look at your properties, what you need to remember is this about your log properties. If you're going to work backwards and go from multiple logs back to single logs, what are the coefficient in front of my logs? Always. Understood, even though we don't write it down. They're all ones. To be able to combine logs, the coefficient in front of the logs all have to be 1. So if you have a number in front of the log, where did he come from? Where does he got to go back to? Back to the exponent. So, here we go. To combine these logs, I've got to get rid of that 3 and that 4. They're coefficient out front, so they had to come back to exponents. This would be log base b of z cubed plus the log base b of x to the 4th. You with me? Now I have coefficients of 1 in front of my logs. I get to combine logs. This will be the log base b of, what does multiplication, I screwed that up. What does addition turn back into? That'll be log base b of z cubed times x to the 4th. Here is the next problem. 1/2 the log of x plus 2 minus the log of x. Well, it's understood both of them are base 10s. You have a half a power out front. If you have a coefficient out front, where did he come from? Where does he got to go back to? Back to the power. So this is the log of x plus 2 to the half a power minus the log of x. And then when you combine, this is one big log, understood to be base 10 of x plus 2 to the half. You could also write that as a square root of x plus 2. Subtraction turns into division divided by x. There's my solution. Does that make sense? Okay? Take a look at the next guy. 3 times log base 5 of z minus 1/2 log base 5 of x plus 2 log base 5 of y. Notice they're all log base 5s. You can only combine like terms. They all got to be the same base. If you have different bases, you're going to have to do something called change of base formula to be able to convert them into same bases. Otherwise, you can't combine them. Now, these have coefficients out front. If they have a coefficient out front, they got to go back where they came from. So this is log base 5 of z cubed minus, the sign stays there, the operation, minus the log base 5 of z plus 2 to the half a power plus the log base 5 of y squared. All my coefficients out front went back as powers. Now rewrite it as one big log base 5, and it's a game. Positive things turn into multiplication, addition. If they're positive, you're going to add them. And addition turns into multiplication, which means they show up on top. That's understood to be positive, so the z cubed is on top. Subtraction turns into division, so there's a minus here. That means this z plus 2 to the half has got to be divided. That shows up on bottom. Z plus 2 to the half power. Now this last part is positive. That's addition. Addition turns into multiplication. Multiplication shows up in the numerator, so then we're going to multiply by a y squared. And there's my answer. And it's a game. Positive things on top, minus things on bottom, positive things on top. And one big log.
So it doesn't matter where they...
Doesn't matter where they show up at. If there's a minus in front of it, the term's going to be in the denominator. If it's positive, the term's going to be in the numerator. Okay? The next one, never forget John's fundamental calculus. Clean up your algebra first. First thing I would do on this problem is distribute the 4 so I can analyze terms. This would give me 4 log base 2 of x squared plus, what's 4 times a half? 2 log base 2 of x plus 4 times 4 is 16 log base 2 of z plus 1. But before we can combine logs, we have coefficients out front. They're going to go back where they came from. This becomes a log base 2 of x squared to the 4th power plus the log base 2 of x squared plus the log base 2 of z plus 1 to the 16th power. Coefficients went back. Now you might as well clean them up. What is x squared quantity to the 4th power? Power to a power? So this is the log base 2 of x to the 8th plus the log base 2 of x squared plus the log base 2 of z plus 1 to the 16th power. Turn it into one big log. But here's the thing, all the terms are positive. So the x to the 8th will show up on top. The x squared will show up on top. And the log base 2 of z plus 1 to the 16th means that z plus 1 to the 16th will show up on top. You might as well combine like terms. What's x to the 8th times x squared? Try again. All right, when you multiply, you add. So this will be the log base 2 of x to the 10th times z plus 1 to the 16th power. And there's my solution. Now, let me explain from a calculus perspective why this stuff is so important to you guys. Okay? Here we go. I'm doing calculus on this stuff. I haven't done a calculus thing yet. Have I taken a derivative, anybody? Nope, not yet, because we haven't taught you about that. That's what the next part of that section 3.1, 3.2. We're going to go back and look at this stuff with the calculus perspective. I got a question for you. Take a look at this guy here. This first one's a great example. You want to take derivative of this guy. He's awful. Look at him. Log of 100x times x plus 3 divided by z times x minus 4 cubed. This is a nasty, nasty function. But if I want to take calculus, remember another one of John's fundamental rules of calculus. It's better to do calculus on easy stuff than it is to do it on hard stuff. If you use your log properties on this thing and bust them up, I got 1, 2, 3, 4, 5 terms. It looks like it's harder, but if I'm going to apply derivatives on this thing, it's pretty simple. And what's derivative of 2? 0. Derivative of log of x is going to be 1 over x times 1 over natural log of 10. It's a formula we'll show you later. But the fact of the matter is, once you got individual terms, it'll be easier to take the derivative of than it is to take derivative of this whole thing. That's the trick and why we're showing you this stuff.
So we want it to be broken up.
We want it to be broken up if I'm doing calculus. We want it put back together again if I want a condensed formula to plug numbers into. So, okay? This is a calculator formula called the change of base formula. Log base b of m equals the log of m divided by the log of base, which is also equal to natural log of m divided by the natural log of b. The purpose of doing this is to use your calculator. Again, reminding you, there are only 2 log buttons on your calculator. There's an LOG button and a natural log button. That's it. So how in the world am I going to calculate something like this? What is the log base 8 of 17, and I want to figure it out to like 20 decimal places or something or other, or at least 5, I don't know, whatever. Well, according to the rules, to change a base, the change of base formula is I get to choose base. The real formula says this. The log base b of m is equal to the log base x of m divided by the log base x of b. You choose the x base. That's what the real change of base formula is out of your textbook. But if I'm going to choose the base, I'm going to use the one that's on the calculator. There's only two of them that are on the calculator. X had to be either 10 or X had to be E. Common log or the natural log, because that's where my buttons are at. That's why I wrote it the way I did. So, for this particular problem, log base B of 17, if I want to use my calculator to find it, I'm going to use, that would be the log of what you're originally taking a log of, which is 17, divided by the log of the original base 8. And I can type that in on my calculator. This will be log 17 divided by log of 8. And all we're interested in is the decimal. 1.36248, however many decimal places you need. But I want to show you something, brother. Whether you chose common log or natural log, I choose E, natural log. This will be the natural log of 17 divided by the natural log of 8. Notice, you get the same number again. You choose the base. Okay? So, and let's calculate this one then. What would the log base 5 of 15 be? Doesn't matter which one you use. That'll be the natural log of the original phone number, 15, divided by the natural log of the original base, which is 5. The answer is 1.682606194. Okay? So there you go. Now, here's the deal. Again, I've still got a lot more little algebra to go through here, but again, I'm doing this as a review. So this is my goal next time. I'm going to go back and start looking at solving exponential and logarithmic equations. Again, as a review, but we're going to be doing this. Logarithmic and exponential equations. And then, again, look at the graph of it. But that will probably take about 15 minutes for us to do all that stuff as a review. This section 3.1 and 3.2 that we're going to be doing again, honestly, is going to be looking at the calculus and the derivative aspect of this stuff. So I'm going to go back and redo all the section 3.1 and 3.2 again, but start taking derivative and limit stuff. So that's what's going to be on Thursday's agenda. See you guys then.